Let's look at an example using the conservation of energy now. So let's say we have a friend and he's going to throw up a baseball. So he's going to give it some initial velocity. Okay? And we know that the baseball eventually is going to go up some height h and then come back down. Okay? So let's say we want to find out what that height is. So how high is the baseball going to go? Well, conservation of energy tells us that the initial energy is equal to the final energy. So in other words, the initial energy is equal to 1/2 mass times the velocity squared. The final energy is going to be mgh, because initially it's all kinetic energy, right? So we could have our potential energy, but in this case our potential term's 0. In the case of the final energy, we could have a kinetic energy 1/2 mv squared, but the velocity is 0. So in both cases, so initially it's all kinetic energy, and at the end it's all potential energy. So now we can just solve this and say that 1/2 m v initial squared is equal to mgh. We see that the masses cancel, and so the height is simply the initial velocity squared over 2g. Okay, so now let's say we have a similar situation. Let's say now our friend throws the ball, but let's say we're up on top of a building, at a height h, and we catch the ball. And now let's say we throw it back down to our friend. We'll throw it straight down with an initial velocity vi. So it's going to go back down the same distance h. Our friend's going to turn around and he's going to catch it. And so now let's say we want to find out what's the velocity when our friend catches it. Okay, so we'll set it up the same way we did before. We'll say that the initial energy is equal to the final energy. Okay, so initially our energy is 1/2 m v initial squared plus mgh, right? Because now here we have a potential energy associated with it. And then our final energy now is just going to be 1/2 m v final squared plus 0, because there's no potential energy because our height is 0 here. So we see that we have 1/2 mass times our initial velocity squared plus mgh is equal to 1/2 m v final squared. Once again, the masses cancel out, and we can multiply everything by 2. So we see that v final squared is equal to v initial squared plus 2gh. So in other words, the final velocity is the square root of the initial velocity squared plus 2gh. This also shows us, let's say we hadn't thrown it down to our friend, if we had just dropped it. Well, in that case, the initial velocity would be 0. And so the final velocity would just be the square root of 2gh. And we see that, that's exactly the same velocity that our friend initially threw the ball up with to get it to go this height h. So one other quick point that I'll make while we're looking at this problem is, let's say we had set this up a little bit differently. Let's say instead we had set this up so this had potential equals 0. So here the potential would be minus mgh. So if we look at this, we see that our initial energy in the first case, so this is the case where our friend's throwing the ball up, so we would have had an initial energy equal to 1/2 m V initial squared minus mgh, and then that would be equal to the final energy, which would be 0 now, because again there's going to be no kinetic energy when it reaches the top, and we define our reference point, so the potential energy is 0 there. Well, you see that if we solve this out, so we'll add the mgh over to the other side, and we solve it to get the exact same answer, V initial squared over 2g. So just like we had mentioned earlier, it doesn't matter where we set our reference point for the potential energy, we're still going to get the same answer. All that really matters is the difference between the potential energies at both points.